Okay.
Okay, we're just waiting for Professor Tour to just join us. Professor Tour, if you're hearing me, I would like to start. If you're ready?
Yes.
Sure. So, good evening, everyone. My name is Murtaza Ali Khan, and I'm the Vice President of the Graduate Student Association. On behalf of the GSA's Executive Committee, I would like to thank you all for joining us today. In order to make this lecture an enriching and educational experience for all, we would kindly ask you to mute your microphones and keep your cameras off throughout the duration of the lecture. Please hold your questions till the end of the lecture. To ask a question, you can either type it in the chat or raise your hand, and we will give you the floor to ask your question in person. We are very honored and very excited to welcome Dr. James Stewart today. Dr. Tour is the TT and WF Chao Professor of Chemistry, as well as the Professor of Material Science and Nanoengineering at Rice University. Prior to this, he has spent more than a decade on the Department of Chemistry and Biochemistry at the University of South Carolina. He has had his postdoctoral training in synthetic organic chemistry at the University of Wisconsin and Stanford University.
Yeah.
His spectrum of research has allowed him to work in from nanoelectronics to conducting green carbon research to enhance oil recovery. He has worked extensively in the field of carbon composites to develop nanotubes and graphene synthetic modifications, including single molecule nanomachines that encompass molecular motors and nanocars, a true pioneer in the blend of polymer science and chemistry. He personifies the excellence of leadership in the community and has developed various educational packages, such as SciRave for one, which is used to implement science-based instruction by over 40,000 teachers and is the most adopted program in Texas. His contributions to the field of nanoengineering and molecular electronics have been reflected widely in his research portfolio, where he has amassed over 150 patents and an H-index of about 152, with over 109,000 citations, and still counting. He was appointed as a Fellow of the Royal Society of Chemistry in 2020 and was awarded the Centenary Prize in the same year for innovations in materials chemistry with applications in medicine and nanotechnology. He was inducted in the National Academy of Inventors in 2015 and was named among the 50 most influential scientists in the world today by the bestschools.org in 2019, a list where he shares his names amongst the likes of Stephen Hawking, Peter Higgs, and Sir Tim Berners-Lee. Dr. Tur, thank you for agreeing to give this lecture to our TAMUQ community here. And now, without further ado, sir, the floor is yours.
Thank you very much. So I'm going to talk to you today about laser-induced graphene and flash graphene. And what I want you to keep in mind is that, well, first of all, if everybody could just check to make sure that they're muted, I'd appreciate that, because I don't want you to be embarrassed thinking you're muted and you might not be. I want you to think in an entrepreneurial sense. What can you do with the science that you develop? And how could these things be extended? So with that, okay. So I'm going to talk to you about laser-induced graphene. And we found that you could take polyimide sheets, which are commercial plastic sheets, and you can convert them into graphene if you hit them with a laser scriber. These laser scribers are in every machine shop. I am sure there are several on your campus right there in Qatar. And it's a very easy way to make graphene. When we first discovered this process, we discovered it in 2013, filed a number of patents on it. And so when you discover something, if you think it could have commercial value, you want to patent it before you publish it. And then we published it in 2014. And now there's about 5 papers per week coming out on laser-induced graphene. So it has become like the method to make graphene if you're going to make it for device type embodiments. And so when the laser hits polyimide, it will convert the surface into graphene. You get a porous structure. Here's the polyimide, and it's about 20 microns thick of laser-induced graphene on the polyimide. and it's this porous structure. It is clearly graphene because it has the 2D band by Raman. There's the G band, there's the D band. The D band is not, in this case, due to a lot of sp3. The D band is here because if you take a sheet of graphene and you just bend it, those carbon atoms along the bend will start becoming sp3-like, and that's what gives you that D band. And it's clearly turbostratic because of this broad X-ray diffraction peak. You can change the parameters, and you can go from a foam to fibrils. And you can, again, it is clearly graphene, but it is more of like a fibril or scrolls type embodiment. And you can draw any pattern you want with the laser. We noticed that when we would do this in the air, the surface would be super hydrophilic, meaning you put a drop of water and it totally splays out. That's due to the oxygen on the edges of the graphene. However, if we do it under an inert atmosphere, then the surface becomes super hydrophobic, has 157-degree contact angle. Anything over 150 is super hydrophobic, and it's very hard to get even a drop of water on there because it keeps wanting to run off. We've done a number of things with this. For example, you take a sheet of polyimide and you drill holes in it with the laser. And then you make one side super hydrophilic, one side super hydrophobic, and you can do oil-water separations this way. Oil will go through one way, water will go through the other way. And so lots of interesting things you can do. It turns out that the super hydrophilic surface, the surface that loves water, is quite antimicrobial. So this is using wastewater, and you can see that the polyimide gets a lot of live organisms growing on it. This is the polymeric organisms polymeric materials that they make, and this is the dead organisms. Same with graphite, lots of live and live organisms and the polymer residues. The hydrophilic surface gets very little, if anything, growing on it. And so you can see laser-induced graphene versus polyimide for bacterial growth. And the reason for that is when it's super hydrophilic, it always has a layer of water on it. And that layer of water prevents the microbes from being able to stick down to it. It's much like when there's a layer of oil on a surface for us, we can't get hold of that surface. You put a layer of water and they can't stick to it. If you get rid of that water, they stick. And the other thing we've done is we've put a voltage across 2 contact pads of laser-induced graphene. You put this in a bucket of wastewater, and you can get a 4-log reduction of the microbial content in that bucket of water at 2.5 volts. So you apply 2.5 volts, and you can get a large reduction. This becomes really important for applications where you have to try to kill microorganisms. Turns out, for example, one of the prime places that people in the hospital get these stomach infections, it's because of ice. The ice makers are where the bacteria congregate in the water that's being chilled to go into the ice maker, because that water is rarely replaced, rarely changed out. You just have new water coming on top of it. And so you could take this and just drop it it looks sort of like a little flashlight. You just drop it in there, and it's generating a voltage across this thing and killing everything in it. So you don't have to do any retrofitting. You just put this in there, and every so often you change out the batteries. We built a lot of devices from this. You can make interdigitated supercapacitors this way. We were getting 4 millifarad per centimeter squared, which was better than graphene oxide-based supercapacitors at the time. You can hook these together in series or in parallel, and you can light LED lights out of it. Then what we did is we brought it through a lot of flexing, so you bring it through a lot of deformation, and even after 6,000 cycles, it retains its behavior, even 6,000 bending cycles. So you can make flexible electronics this way. We've made stack structures, so we run on both sides of the polyimide. You run on both sides, and then you can stack it up. We put an electrolyte in between, and you make these stacked structures. So here's the polyimide, here's laser-induced graphene on both sides. And you can hook them up in series or in parallel, in series or in parallel. You can bring them through 4,000, 6,000 bending cycles, and they still work just fine. So again, very good for flexible electronics. I mean, this, just hear me out here. This has got application written all over it. This is where you want to start companies. When you have something that can translate into applications this quickly, it's a very big deal. And then just to show you where we came, you can make pseudocapacitors out of these by doing electrodeposition on some of these surfaces. And if you look at the Ragone plot, a Ragone plot plots energy versus power. And batteries have very high energy, but very low power. Capacitors have very high power, but very low energy. What you want to do is you want to be up in this quadrant. You want to move toward this quadrant where you can have very high power and very high energy. That's supercapacitors. Here's a commercial supercapacitor. Here's a commercial activated carbon supercapacitor in black. Here's where our LIG supercapacitors are. And they are really pretty good. And there's no lithography here. These are just made so quickly. Where we came is we started out at 4 millifarad per centimeter squared in area capacity. But we went up 250-fold. And now we're up over a farad per centimeter squared. Power density, we've gone up over 10-fold. We've gone up 10-fold in power density. And so this is by volume. So you see that it has really good properties here. And then we learned you can do it on a lot of different surfaces. At first we thought it was only polyimide, but then we learned we could defocus and you could do it on all sorts of surfaces. And so lots of different surfaces can be used. You can even use cellulose. Cellulose has lignin in it, and that lasers quite well. You can do wood. Wood would normally ignite, but if you do it in an inert atmosphere box, it makes laser-induced graphene just fine. Then we learned you can just use flame-retarded wood. You buy wood that has a flame retardant in it, and it doesn't ignite anymore. Then what we learned is that for other surfaces, what you want to do is you want to run defocus. So for polyimide, you want to run focus, but for other surfaces, the first hit of a laser will carbonize it, turn it to carbon black. The second hit will make some graphene out of that carbon black. The third hit will make all graphene out of it. So you can either lase it multiple times or just defocus the laser. If you defocus the laser, now you have overlapping spots. So you see each one of these spots has had 3 or 4 hits on it just because of the defocusing of the lasers that goes along. So when you defocus the laser by 1.4 millimeters, that is equivalent to lasing 3 times. And so we can write on paper. Now, paper would normally ignite in air, so we just spray it with a flame retardant. You can get flame retardant for paper. You just spray it, and it doesn't ignite. So this is a piece of cotton paper that we've written rice on it. This is not dropping graphene on top of paper. This is converting these cellulose strands into graphene. You're blowing out the oxygens and forming carbon. Here's cork. Here's bread. So you can just take bread and you're converting the carbohydrate strands into graphene. You can do this on cardboard. You can do this on a potato. And you say, well, why would you want to write on food? Well, why wouldn't you? I mean, this is important because what you can do is you can think of marking every item, just like you might have stickers on every apple. I mean, lasers write faster than you can apply a sticker. In fact, every plastic bottle in the United States that you drink water out of has a little laser scribe thing on it that marks the lot number. If you can build sensors into a potato, then you could know what field it came from. Is it really local, or did it come from some faraway country? You could put sensors on there to tell you if it's been heated up too hot in transit. You can put a salmonella sensor on it. You could put an E. coli sensor in it. We took coconut. We made supercapacitors on coconuts. You can write on coconuts. It's no problem. These all convert the surface into graphene. You want biodegradable electronics? Here it is. We've done a lot of different reactions on this. We can split water, for example. You can take one surface and another surface, and you can treat them differently. So in other words, you what you do is you lase the surface, and then you draw cobalt phosphide on the surface, and you lase again. You put you lase the surface, and then you put nickel and iron on the surface, lase again, or you just electrodeposit. This is one sheet of polyimide. We put a pinhole here to allow equilibration, and we put a voltage across it. So if you put that on two sides and you have your polyimide sheet in here, now when you start applying a voltage, you get hydrogen coming out of one side, oxygen coming out of the other side. So it's already self-separated in the water splitting to hydrogen and oxygen just by applying a voltage with a very low overpotential. So you can see the parameters here. Lots of devices we've made out of this. Now, this has all gone commercial now. We have 5 PCT applications. PCT means worldwide filing. You choose the countries you want. We don't normally choose Qatar because it's just such a small market. We choose, for example, you choose the US, and then you choose the EU, and we'll choose several countries in Asia. China, always China, it's a big, big market. And then Japan, Taiwan, we will choose, and that's outside the PCT domain, so you have to choose that separately. But here's the first product coming out. Sits on a tabletop, and it sucks air in. It sucks air in. So as you're talking across this table, it's sucking your air in, and it blows fresh air out the top, comes out the top. And so it's as if you have a sheet of graphene between the two sides of the table. You put this on a countertop, nobody's wearing a mask. When she speaks, her air is getting sucked in. He speaks, his air is getting sucked in, and fresh air is being blown out the top. This is good for students at desks, these big corporate spaces where you're just separated with 4-foot high cubicles, these little barriers. And so that's where we're gonna go. We've built lots of air filters. We have publications on this. And now remember, I don't have to do anything anymore. There are 5 publications a week coming out in the literature using laser-induced graphene. And guess who owns all of that? Guess who owns all of that? Because we filed patents on this long before we published it. If you're making laser-induced graphene, you make a device out of it, you're going to have to get a license to be able to produce whatever device you want. This is what I want you to think about. Think about these things in an entrepreneurial sense. We signed a joint venture so we started this company, LIGC Applications. From this is going to spawn, I don't know, at least 5 companies, maybe more. One of them was just for air filtration. We signed a joint venture with a Chinese manufacturer. So they bought half the company, but only for air filtration. So they get half of the air filtration market, and we want them to have a lot of the company. They had to pay for it, but we want them to have a lot because we don't want them trying to work around us. We want them to be incentivized. You make this company great, you'll be great. And they have all the manufacturing capability. So we don't want to have to build a manufacturing plant. Look at this. They built this, and it sits right on the table. It looks really good. It's packaged like an iPhone. I mean, really high quality packaging. You can have a little cubicle, and it's just sucking huge amounts of air into this thing and purifying. So it's called viral wall. So think entrepreneurial when you're doing your science. All right, graphene in bulk. So that's graphene on a surface. If you're going to do graphene in bulk, this is how it's produced commercially. You grind up graphite, and it goes into this grinder. And then when it's small enough to get through this filter, it goes on through. And then the smaller ones come out the top. These are called graphite nanoplatelets. The bigger ones go toward the bottom. The biggest producer in this method is XG Sciences, came out of Michigan State. They're making about 6 tons a year. Everything they make is purchased. The price of graphene, bulk graphene, this is different than what I just showed you. That's laser-induced graphene on a surface. And then you have other applications where you want bulk. The price is $60,000 to $200,000 per ton. To put that in perspective, a ton of high-density polyethylene is about $2,000. So this is $60,000 to $200,000 per ton. And everything that is made is purchased. If you own a Ford car, motor vehicle, all Fords ever since February 2020 have had graphene in them. They're in the foam seats, they're in the foam insulation, and they're going into more things if the price comes down. So what we discovered this in 2018, that you could put carbon across between two electrodes, any carbon source, read my lips, any carbon source, and you put a voltage across this, it will heat to over 3,000 Kelvin in less than 10 milliseconds. And at those temperatures, every bond in the system breaks. And then the carbons reconstruct into graphene. You get a bright light coming out. Here's a quartz tube around this. A bright light comes out. That's where all the excess energy comes out as bright light, black body radiation. And the quartz tube, after this reaction, it's done in 20 milliseconds. After this reaction, the quartz tube is only warm to the touch. It's not even hot because all the energy has gone into the samples. It wasn't hot long enough to get heat transfer to the quartz tube. So we built several different versions. This was the version 2.0 that we had built. And there's a bank of capacitors down here. And here's the reaction chamber, which is just a vacuum desiccator. And we built this out of wood that we had cut on our laser scriber and then epoxied it together. You see, these are just two brass screws that come in. They're not tightly fitting inside here, so gas can come out. And you just put the voltage across it. This is where we published our first paper based on just what we got out of that thing. We built a spectrometer so we could measure the temperature. How do you measure temperature at these high temperatures? You do it spectroscopically. So we built a spectrometer to do that. And so you see that we can record these temperatures. This is hitting 3,500 Kelvin in a matter of about 5 milliseconds. And then we turn it off after about 10 milliseconds, and it cools very rapidly, which is really important as well. And so when we first published this, we showed we can use carbon black and we could make graphene. This is the best spectrum of graphene that anyone has ever seen. But this is the representative spectrum that we get. We run the Raman map over a large region, and we can use coal. Now, anthracite coal is about $100 a ton. So think about these economics. $100 a ton in starting material, $100 a ton in electricity. And we're making something that sells for $60,000 to $200,000 a ton. Think about those economics. All right. Calcined Coke, which is an oil product. Coffee. This is spent coffee grounds. Coffee is a carbohydrate, C6H12O6, so it's only 40% carbon. We can get 35 out of that 40%, so waste food. We've gotten this price down to about $35 a ton now. What we make is we make turbostratic graphene versus Bernal stacked is what you get from the exfoliation of graphite. Very hard to pull these layers apart because the hot part of this benzene ring below sits in the middle part of the cool part of the benzene ring above. And so these stick rather well, hard to pry apart and get them mixed up in composites. But if it's turbostratic, it never had time to align between the layers. And so it disperses much better in composites. And then you can tell spectroscopically by looking at the TS1 and TS2 band, or the turbostratic 1, turbostratic 2 bands. Missing M peak tells us that we're turbostratic, that they're non-aligned layers. We've studied the different voltages you could. We studied the different resistances. So as you push those brass rods together, the harder you push them together, the lower the resistivity in the sample. And you want this, there's going to be a sweet spot for getting the optimal resistivity. And then you can scan voltage versus the 2D to G, the spectroscopic features, and the D to G band. You can look at temperature. 3,100 Kelvin is better than 2,850. And at these temperatures, this is why it's self-purifying. It's self-purifying because even aluminum, silicon, all of those are subliming out at about 2,700, 2,600 Kelvin. The only thing left in there is carbon. Carbon doesn't sublime until about 3,600 Kelvin. And so carbon is what stays. It's self-purifying in that way. You look at temperature versus time, you look at cooling rate, how fast that these can cool, 30,000 Kelvin per second cooling rate. And that's what you want to be able to do. And then you look at different pulse lengths, pulse times, 2 pulses, 1 pulse, and so forth. You can get different size distribution just by looking at different sheet sizes that you want, depending on starting material size, depending on how long you run the scan. If you're flashing it for 10 milliseconds, you're going to have small sizes. If you flash it for 500 milliseconds, you're going to have larger. For half a second, they're going to grow larger. So you can change sheet size. A lot of times you want small sheets when you're making composites. This is clearly a hexagonal pattern. It is graphene. It's a hexagonal pattern, and it's got little spots here all the way along that tells us it's hexagonal, and they're off. They're shifted, so it's turbostratic. We've done a lot of modeling, and when you heat things up to these temperatures, every bond in there is going to break, and then it's going to reform as graphene, which is the thermodynamically most stable carbon formation. So this is kind of the genesis. So the student put a capacitor, 2 leads, some carbon in the middle, and flashed it. That was where he started. I don't know why he used a metal bench, but a metal cart, but he did. And then we went to the version 0, and here was the holder for version 0. He just strapped these two together with electrical tape to do the pressure. And then we found we could buy little vices from Amazon. This is a little vice that you buy from Amazon to do this. And then that went to flash version 1, and then flash version 2, which I showed you before. And so anyway, now on that flash version 2, we could go up to 1 gram at a time, a 1 gram batch. And if you take commercial graphene and you put it in, you suspend it in solution and then centrifuge, everything comes out. Not with our stuff. It's much better suspended. You can put this in plastics and it will greatly increase the strength of the plastic, really toughen it up, even better than carbon black does. We can add 0.1 weight% of flash graphene to cement, and it's 35% increase in the compressive strength, 19% increase in the tensile strength. That's a big deal. The reason that's a big deal is because concrete is 8 to 9% of all CO2 emissions in the world come from the making of concrete. You take metal carbonates, you heat them up to 2100 centigrade. They form metal oxides, and you're blowing out CO2. Then you had to heat that furnace to over 2000 C, so you're blowing out CO2 on that. Then you put that concrete in a truck, you add water, a lot of water, it's very heavy, and you ship that off to a site. 8 to 9% of all human CO2 is from the making of concrete. If you could use 1/3 less concrete, that's a big deal. This is where we are now. This is just 48 capacitors in these wooden boxes. There's 4 wooden boxes here, 48 capacitors. They're all wired up. This is all built in a framework in a hood. This is the reaction chamber. We pulled a mild house vacuum to help with outgassing, but now we don't even use a vacuum. There's enough outgassing to keep this protected. Some electronics in the hood, some electronics under the hood. Here was the display on the computer. You can power it up, start charging. If you want to discharge, you can push here. It'll drop it across a load resistor. Or you can flash it. You can set the time of, this would be 1,000 milliseconds, so 1 second. Now what we've done is we've built an automated system. So during the COVID shutdown, so from about this time last year, March last year, until end of May, we were shut out of our labs. So we didn't want to let that hold us back though. So I bought a bunch of 3D printers, and I had the students making parts, designing things and making it. I sent electrochemistry setups home with them. So they're just using aqueous solvents. We were doing electrochemistry, and we did as much chemistry from our homes as we could during the shutdown. So now what we do is we start with 5.7 grams of coal per batch, and we flash and we get about 5 grams out because coal has a lot of hydrogen. We put them 350 to 400 volts. Our graphene yield is 90%, our process yield is 90%, our graphene yield is about 100%. And so we have this automated flash unit, and this is what it looks like. There's this load port, and these come rolling on down. They're set in here. This is the piece that lifted it up. Then this will drop down, and then this will move across these. It'll move forward, and then this will flash, and there's what the flash looks like. And then it'll separate, and it'll drop that down in the water there. And so that just repeats over and over again. This takes about 2.5 minutes to charge up the capacitors. That's the slow step. So we're fixing that now. But you get very high quality graphene out of this, and this is bulk turbostratic graphene. So now what we're doing is we're going to a 20-second charge because we're bringing in a higher voltage. We're bringing in a 308 volt line. We built all of this in here is built in this box. Here's a load resistor. This we got from eBay. We buy a lot of our parts from eBay. And just it makes things a lot easier. We buy plastic boxes, build all our own electronics. Here's 2 fans here, another fan here. And so we build all of this stuff ourselves. And so I've got really good students that can do this. This has been our rate of growth. You've heard of Moore's Law. Well, this is Dewey's Law. This is the student who developed this. Our production rate capability doubles every 9 weeks. So every 9 weeks, we're doubling our production rate. This is where the Department of Energy wanted us to be. We can do that. We can deliver that. And so now we've built a company around this. Remember, I want you guys to think entrepreneurial. We built a company around this. We filed patents before we published. Then we published, built a company called Universal Matter. And they hope in 14 months to be doing a ton a day. And then it's going to scale from there because these are easy units to build. Lots of different designs we might consider. But this is, we started it in the US and Canada. So we have Universal Matter Limited, Universal Matter Inc. And there's the website, universalmatter.com. If you went there, you could see movies about this and see all that they're doing. This company is taking off like a rocket. It is just amazing. So exciting, so exciting. Now we're going into concrete, we're going into asphalt. It has been known that you can strengthen concrete, as I showed you. So we've got contracts with the biggest concrete companies. Asphalt, it's great for asphalt. Could never come in at the price point, but now it can. We're going into paints, wood composites, steel, as long as you got to watch your temperature curves on that. Aluminum, even a GMP line for bone composites. Now, where's energy going to come from in the next 20 years? Where's that energy coming from? Well, today, what we do is you combust, in this case, say natural gas, and you make CO2 and water. All right? So you're making CO2 and water in this thing for natural gas and burning of natural gas. And then what you're going to do later on is what you could do is you could take methane and strip all the hydrogens off it. You could do that. And then you get carbon solid. And then you take that hydrogen and you mix it with oxygen and that you get water. This is a fuel cell. If you look at the thermodynamics of this is 800 kilojoules per mole. This is 400 kilojoules per mole. So half the amount of energy comes out of this as comes out of this. But this is thermodynamics. In actuality, this is 80% efficient, this fuel cell reaction. This in an automobile is about 25% efficient in the city, 35% efficient, maybe 40% on the highway. And so you get a lot of that back just due to the difference in efficiency. This process has been known since the 1950s, called furnace black. They just didn't know what to do with all that carbon because humans generate 30 billion tons of CO2 is emitted each year through combustion. That's what humans emit. If you just look at what's the carbon content in there, that's 8 billion tons of carbon. So if instead of emitting CO2, you emit carbon, You just have carbon, you're getting rid of those two oxygens, so that's 8 billion tons of carbon. They just didn't know what to do with all that carbon. Well, of course, we know what to do with it. We're going to turn that into flash graphene. And then there's also mobile storage and how will we use hydrogen as a fuel. We got ideas on that as well. But if you have 8 billion tons of carbon, that's 8,000 million tons. Here's 44,000 million tons of cement and concrete. Concrete and cement, they swamp all other building materials combined. You could put 8,000 million tons of carbon in 44 million tons of carbon today. So you could do this. And so the nice thing about this is an amazing form of carbon, which we'll talk about in a minute. There's also a problem of the human footprint problem of waste. 30 to 40% of all food in the world is thrown out. And it has to be because it goes bad. That's really nasty in a disposal site because it doesn't just form CO2. It forms methane. And methane's a much more severe greenhouse gas than CO2. Plastic waste is a big problem. Rubber tires are a big problem. So what we have shown is, here's the mismanaged plastic waste. So mismanaged plastic waste, the US is not too bad. Asia is the killer on mismanaged plastic waste. I mean, it is just so destructive. And so that this mismanagement means that it just gets thrown out and mismanaged in the sense that it ends up in waterways. And this plastic lasts a long time in the oceans. A plastic bottle can last 450 years in the ocean. I mean, a coffee pod, 500 years, that's a long time. So it comes out of Asia and it forms this plastic vortex, which is around Hawaii in the Pacific. And this is bigger than the state of Texas, 10 feet thick. Just plastic. And it's a mess. It's an absolute mess. And you can tell from the plastic that it's come off of Asia because the currents move in this direction. And what are you going to do with all of this? Well, how about upcycling waste plastic using flash Joule heating to graphene? We put $30 per ton in electricity costs, and that's it. There's no sorting. Recycled plastic costs as much as virgin plastic because of the human sorting that has to be done. There's no sorting. We can do it on mixed waste plastic. They will take the plastic before recycling and they will wash it 3 times with water and detergent. That's a lot of water, hot water and detergent. We take no pre-washing. It's unaffected by plasticizers, dyes, adhesives, food waste, organic and inorganic fillers, doesn't matter. No solvents, no purification is needed, self-purifying, and no low-value ash is left over. Encouragingly, graphene is non-toxic. It's naturally occurring in the environment. It's graphite, when it shears off in lake beds, it releases graphene. Its agglomerates are the natural mineral graphite. It's a terminal natural sink for carbon. It's one of the few times you'll ever bring up carbon assets from under the ground in coal or in oil or in natural gas, and it's not going to eventually become CO2. You know, go in fertilizer, it's going to become part of a tree. When that tree dies, it's going to turn into CO2. Not this. It's going to stay for at least hundreds of years under most conditions. Now you can get it to degrade, but under most conditions, it's not. Look at the graphite's geological stability. It can be used in composites of all kinds, and at the current price of 60 to 200K per ton, there's a lot of incentive to do something with this. We have taken all sorts of foodstuffs and proteins and coconuts, we turn them into graphene. This was done in our first publication. Look what we've done, how good we can get this. This is any type of plastic. Polyethylene terephthalate, high density polyethylene, polyvinyl chloride, low density polyethylene, polypropylene, polystyrene, doesn't matter. We can mix them all. Beautiful graphene. We can take rubber tires, $30 a ton, turn it into graphene, or tire carbon black, turn it $30 a ton into flash graphene. This is an example where we took actually end-of-life vehicle plastic. So this is from Ford Motor Company. Ford, the auto companies are now going to be held responsible in Europe to deal with all the plastic waste that comes off of their automobiles at the end of the lifetime of the automobile. It's not the problem of the consumer. It's the problem now of the auto manufacturers. There's about 175 kilograms of plastic in vehicles right now. Ford sent us some end-of-life vehicle plastic. This is the plastic that's on wiring. It's from seats. It's from cushions. It's from insulation. It's from rubber seals, and it was just all mixed up and dirty. It came off of a landfill. Dirty stuff. We put it through a hammer mill. We add 5% met coke, which is a coal product, to give it conductivity. We built an AC/DC flash system, which really gives us higher versatility. And we can make nice graphene out of it. Boom, nice graphene. We send this back to Ford. Ford put it in their urethane foams, and they see a 20% increase in the compressive force if they add 0.01% of graphene into their foam. If they add 0.025% or 0.1%, you can even see, was it a 34% increase? This is what they wrote, 34% increase in the Young's modulus at 0.1%, all right, 0.1% in their foams. So we're actually able to take end-of-life vehicle plastic and turn it into graphene, which can go back into plastic and strengthen the plastic. So you use 20 to 30% less plastic, which really lightens up the weight of the vehicle. You know, for vehicles right now, it's all about light weighting. And then also you can replace aluminum with metals, with plastics that have graphene in it. So this is a very big deal. And so we're looking at all these potential markets. So that's what I want you guys to think about. Think entrepreneurial. What can you do? And this graphene company is going great. And you say, well, how do I have how am I able to run all these companies? I'm glad you asked that. I don't run any of them. And I don't want to. I don't want to be a CEO. I don't want to be a chief technology officer. I got my lab. I want to be a professor. I want to teach my classes. I want to do my research. Once you're part of a company, you got to work. You're an indentured servant. You're a slave to that company, and you're a slave to people who have money. That's not what I want to do. So I just get some founder stock, a healthy portion of founder stock. I teach them how to do it. And then the investor groups, it's up to them to hire the CEO, to hire everything. And I don't have to do anything. This is why I have 14 companies, and I just have stock in all the companies. They go public. My stock converts into public stock, and I can cash out after 2 years. I can cash out, and if I want to, or I can leave it in there and let it ride. And so you can do all of these things because I can't be a professor and run a company. I can't do both well. In fact, I would generally do both poorly if I tried to do that. So I just let them run the companies, and then let them take it away, and I get on to the next thing. So that's what you want to do. I'm never an officer or a director in these companies. So that's the way I do it. And you can be quite entrepreneurial. I used to license all the intellectual property to big companies. I don't do that anymore, because that's the way you make nano dollars that way. You make very little money because the big companies sit on the technology, and you just haven't, and they're not inspired to really make this thing work. A small company, you get founder stock and you own a good chunk of that small company. That's the way you really make money. And so we start a lot of companies. Early on, it's, the big thing, it's hard for academics to properly identify what's worthwhile. Some academics think you can see a blip on an oscilloscope and it has great value. That has zero value. You got to be able to put something in a box that you're going to sell to somebody. And you don't want any technology that's too hard. You don't want anything that's really fancy, real hard. You want simple things are what get marketed much more rapidly. So with that, here's the group. This was funded by the Department of Energy and the Air Force Office of Scientific Research. Boris Jakobson's group did the computational work, and Rusbah Sheshavari did the concrete work. Here's Dewey Long. He was a student in my group. Now he's a postdoc. He'll be leaving in a few months. He's the one who discovered this process and really made this thing happen. He's an applied physics student from Vietnam, and just amazingly creative. Remember, in this business, it's not how smart you are. It's not. It's how creative you are. The people with the creativity win. And creativity is not something you get just from being good in exams. No way. Creativity is something that's much harder to identify. Paul Avincula has done the rubber tire work. Wei-Yin Chen did some of the inorganics, and this works with molybdenum sulfide to make 2D materials. Walla has done all the plastics work. Bing Deng has done some of the other inorganics that I haven't shown you. And Kevin has done the carbon ash, and he's made C13 graphene. And Carter is just an instrument wizard. And he helped Dewey build a lot of this equipment. So that's the group, and that's the end of my talk, and I'll take questions.
Thank you so much, Professor, for this wonderful talk that you just delivered to us. So everyone, the session is open for a brief Q&A. As I said previously in the chat here, you can either raise your hand and I'll direct you to ask a question, or you can ask a question via the chat option, or you can send it to me privately. Professor, I would like to start with an anonymous question that I've received here. In a world that seems to be conservative towards embracing new technologies, especially in the energy sector, what are the marking strategies that are intended to be used to promote the use of laser-induced graphene?
Laser-induced graphene, well, laser-induced graphene is not directly an energy play, other than the fact that you may want to build some devices where the laser-induced graphene turns out to be a lightweight conductor, high surface area material for you. So the laser-induced graphene, if that's what you're specifically talking about, as opposed to flash graphene, that is not a direct energy play. It's a material that can help you if you're building a photovoltaic. It's a material that might help you if you're building a water purification system, but it's not a new energy source in itself.
Right. Thank you, Professor, for answering that. Any other questions, ladies and gentlemen? We have a bit of Professor.
I have a question.
Sure, Professor. Professor Abdullah, please go ahead.
Thank you. Thank you, Professor, for excellent presentation, and congratulations to you and your team for, again, another breakthrough in the graphene arena after the tour method for GEO that I think people around the world use now. And a few of my students actually preparing graphene using the tour method now, use it for different applications. I have a question for the laser-induced graphene. You mentioned that it has antimicrobial activities. My question, do we know basically what's the mechanism for the antimicrobial activity? That's the first question.
Yeah, it's when you put a voltage across it, it generates hydroxyl radical, which is the cleanest way to kill microbes because there's no chlorine, and you're killing microbes with hydroxy radical, which is actually what our macrophages do to kill invading organisms. So they use hydroxyl radical. And so, because the byproduct of that then is water. So that's the mechanism.
Okay, so this could be a very interesting method for membrane surface treatment.
Absolutely. So we have a strong collaboration with Ben Gurion University in the southern part of Israel. And that's the second product that's being developed. It's the membrane, the membrane in these water filter systems. So they have their whole, Israel has its water resource center there in the desert just south of Ben Gurion University. I've been there several times. And we have, we discovered this process, we filed some patents, and then some other patents we filed along with Ben Gurion University, just capitalizing on their water expertise. But that's absolutely right. It can have great applications. It has great applications also in these solar heaters for distillation, where the black just sucks in the heat. It has a high surface area, and it is super hydrophilic, so it wets extremely well, and just a lot of water comes distilling off of this surface. So for purification systems. All of these things are being explored. We have a lot of patents in that area. We welcome other people to work in that area. It's just that when it gets commercialized, you're going to have to pay us a visit.
True. So just a follow-up question, because this is an area that we're working in, actually making, basically using graphene and other material for enhancing membrane performance. So my question, can we control with the laser-induced graphene technique, can you control also the Z dimension, the depth? So how thin can we actually make this treated layer? Because in a membrane, we need this to be
so
really
if you just take your typical laser on polyimide, you get about 20 microns thick. We have gone as thick as a couple of millimeters. You can go up to about a couple of millimeters. How thick we've gone up to. If you want more material there, we've gone as thin as that's a paper that's right now under review where we do this with photoresist, and then it's much thinner. It's probably on the order of sub-micron thick. So you can vary depending on the technique that you would use, the thickness you would get. Now, once you get above a couple millimeters, you're not going to get any more because the laser light is now absorbed and it can't get down to the bottom surface. But what we have done is we've lased from both sides of a polyimide sheet, and then you can get these permeable filters, and we've published on that. The other thing that we've done is we've used laser-induced graphene to print 3D. So you put you make LIG, and then you make another LIG layer, you put it on top, and then you lase the top half, and it builds up the layers. Again, that was work that's already been published. That was, in fact, Dewey Long is the first author on that as well. And I think that came out in ACS Nano a few years ago. So you can even make 3D structures, and the 10 micron laser will build up the graphene. If you use a 1 micron laser, which also are in these systems, that ablates graphene, so then you can cut back into it if you like.
Okay, very interesting. I think Murtaza, is there time? Can I ask another question?
Sure, Professor. Go ahead.
Yes. So I have a question for basically the bulk graphene, the flash induced graphene. You're targeting basically asphalt and cement. So this is actually, I think the price basically going to be a big factor if you're going to actually penetrate this market or not. So what's the price target that you think in maybe a few years you can reach for?
You know, I'm not part of the company, so I haven't read their specs for a while, but they have already, they've not sold anything, but they've distributed a lot. And so the strategy is this: when you sell your product to a customer, whatever they do with it, they do with it. They get a license to use it just because they bought it from you. Not so in this case. When we give it to them, in order for them to get it, they have to sign a joint venture agreement. And in that joint venture agreement, the company, Universal Matter, will own a part of what they do with it. And so that's why the company isn't selling anything. There's so many people that want their hands on this stuff. And the company is, you know, they're sending out hundreds of grams a day to different companies and lots of joint ventures. I don't know what, they haven't yet set a valuation because, you know, once you set a valuation, that's kind of written in stone, and they haven't yet set a valuation, but it is, from a monetary side of the growth target, this is the fastest growing company I've ever been a part of. The company's about 14 months old, and it's got about 10 or 11, 12 employees now between Canada and the US. And but we're talking its valuation is going to be set quite high when they ultimately do a Series A. They've only raised about $7 million, $6 million total, and they don't want to raise anymore because we've gotten over $20 million in federal grants from Canada and the US. And when you get it in grants, you're not giving up equity in the company. So it's a great way to raise money, because everybody's throwing money at this because of the plastics problem, because of the carbon waste problem, because of the food waste problem. And so that's what they're doing. But the target production rate is to have a facility generating 1 ton a day of flash graphene from I believe it's going to be from a coal-derived product, and that's in about 14 months. They're supposed to have that. But then these units, there'll be these big pistons firing, and you just blowing stuff out. Each piston would be resonant time of maybe 1 second, and you'd have many of these pistons firing. So the targets here are quite ambitious, but it's up to them. Make it happen and send me the check in the mail.
Okay, thank you again, and hopefully next time we'll have you here in Doha, basically giving a seminar live.
Oh, okay.
Definitely, Dr. Abdullah. We would love to have you, Dr. Tour, in Doha next time.
Thank
Let's move to more questions. We have Professor Kakosimas who would like to ask a question. Professor?
Thank you, Professor Tour, for your amazing presentation and inspiring for both our students and ourselves. I would like to ask you a question that you don't usually read from the papers or even the patents. How do you balance the safety challenges with the creativity of research and students? We saw many of your lab configurations, and I mean, it's really creative, but sometimes, I mean, you have these concerns about safety, etc.
Yeah, I think about safety all the time. That's probably the thing that concerns me the most. It really governs my prayer life. We have safety discussion every group meeting. Just like in industry, you talk about safety every meeting. We do the same. We've done that for 20 years almost. Every group meeting is starting with safety. On those flash graphene apparatuses, we have several safety measures in place. We have lights that are shining when the capacitors are charged. We have strict orders. Nobody can go into the capacitor bank area unless they've been approved by Dewey or Carter to look into it. We have strict protocols to ensure that the capacitors are discharged before you ever stick your hands into the system. We have rules that you have to wear thick rubber gloves as a last resort before you ever use that system. The whole time you're using the system, even if you're just using thick rubber gloves that extend up to your elbows, so that even if you were to touch the leads, nothing's going to happen to you. And we have strict regulations on that in the group. That doesn't mean that everybody's always going to observe those. And so all I can do is just say, here's the safety constraints we've built in, and we stress safety all the time. And I pray that nobody gets hurt. These wonderful people come to work for me. Their parents send them to school here. And, if they come with 2 eyes, I want to send them home with 2 eyes. If they come with 10 fingers, I want to send them home with 10 fingers. And so safety is a big concern for me. We have to do our work, but we take it very seriously. That's what we do, and we make safety a part of our culture. We have a complete lab cleaning from top to bottom every 4 months. And then we call in then I inspect it. Then we touch up any areas that didn't pass. And then we call in the university to do a complete inspection every 4 months after we've cleaned it to make sure that everything is up to speed. We have the university engineers, electrical engineers come in, the people who run the big electrical systems for the university, where we take actually natural gas and convert it to electricity for the university campus. We have them inspect our apparatus. And so that's what we do. We take it very seriously.
Thank you very much, Professor. Professor, we have an anonymous question here. So the energy sector that you mentioned earlier was one of the examples for which you believe that graphene could, for example, find its application. But what about other sectors, for example, manufacturing? As you have mentioned about big companies that they are not using like the graphene, but you have smaller companies which are embracing this technology. So is there any future plan in place to expand the use of the graphene from a more commercial perspective?
Oh, the graphene's going, every partnership that Universal Matter has is with a big commercial company. I just said I don't want to license directly to a big company, or else you lose, it gets lost in the big company. They change directions and now it's caught up in there. I mean, I have so much of my IP tied up in big companies that are not doing anything with. When I said I don't deal with big companies, I meant I don't license to them. But once we have the small company, they're only working with big companies. These are biggest concrete company in the world. These are big wood companies in Canada. Canada's biggest product is wood. These are big companies that we're dealing with on asphalt. Biggest asphalt company in the US is what we're dealing with. There's big interest from big companies, not just small companies, on this graphene. There's big interest on laser-induced graphene from big electronics companies. So we'll deal with big companies. You're just not going to own the IP. This is big. This is in energy, but it's in manufacturing. It's in clean tech. It's the whole green objective. This is hitting every sector, medical sector, on the graphene. Batteries. I have a battery company, and you use graphene in batteries. I mean, so all of this is there, and it's something that is growing. So if I gave you the impression that this is not hitting every sector and not hitting every size company, I'm sorry about that. In fact, Universal Matter is reluctant to do joint ventures with other small companies just because the prospects for the big company and their tentacles of how big it could be are much larger, and they only have so much ability to interface with people. So, but they're working with the BASFs, they're working with the Ford Motor Companies. I mean, it is big time interest. And this is gonna, Ford, like I said, every Ford has graphene in it. They're gonna be putting a lot more graphene now because the price is gonna go way below $60,000 a ton. I don't know, it's not gonna come down to $1,000 a ton, no way. I mean, I don't know where the price point's gonna come in, but maybe $10,000 a ton, $12,000 a ton. And then at that price point, we will take all the graphene business in the world. I mean, every graphene company is sweating bullets when we start producing because nobody's going to be able to compete with us on price.
That was very aptly put and nicely put. We have a moment for one final question. Would anyone like to ask? Anyone from the students here? Any of the attendees? Okay. Professor, in that case, then I would like to ask the final question. We are all graduate students here who are trying to find our way in different industries, different paths of academia, and trying to figure out at this very young age on how to go about with life. What would be one piece of advice or a word of wisdom would you like to share with us who are very curious about going further ahead in life and to perhaps achieve on the same sort of trajectory in life to reach positions of academia or industry, or in a more better put word, I would say, to achieve that success? What would be one piece of advice would you like?
Okay, well, you're going to take me into things that are more philosophical, but that's okay. One thing I would say is value your family. Don't trash your family to advance your career. I have a wonderful wife, been married almost 40 years. We have 4 children, and we invested a lot of our time and our life into those children. And as hard as the career is to make it launch and to take off, my family was always there to support me. So I would say value your family. The other thing is that you build relationships with people. The whole scientific community is about relationships. So you build relationships with people. It's very important early on in your career to get to know people, to build relationships, to meet people, and do small things that they'll remember you. So one of the things that I've always done, that I do to this day, is I write handwritten letters to the people that I meet that I feel that I have to help them to really remember me. I'll write them a handwritten letter, because if you send an email, it just blends in. But if they get a handwritten letter from you, it means something, and you're building relationships over the long term. And what young people have lost, I think, is they don't appreciate how much relationships can get you. And I'll finish it up with this. I'm a person with a deep faith in God. I have a deep faith in God, and that means a lot to me. And I'm a person of prayer, and I'm a person of the Bible. And so I read and meditate on these passages because men with much more wisdom than myself have written on these pages, inspired by God, and I learn a lot from them. And I believe in prayer. I believe God answers prayer. And I've prayed a lot for my career, And I pray that a lot. You know, there's a man in the Bible, his name is Bezalel. Moses hired him to build the tabernacle. And it says, God called Bezalel by name, the son of Uri, the son of Hur of the tribe of Judah. So he knew God said, I know your father, I know your grandfather, I know what tribe you're from. It says, and he filled him with the Spirit of God. So he's the first person in the Bible who it says was filled with the Spirit of God. He says, I filled him with the Spirit of God in wisdom, in understanding, and in knowledge. Interesting, knowledge came last, wisdom came first. To work in gold, in silver, in bronze. So he can work in all three metals. To work in wood, to work in stone cutting, in stone setting, to work in fabric, to work in perfuming. And he gave him the ability to teach it. The man was the Renaissance man. And I prayed, Lord, make me like Bezalel. Let me work across many different areas. Make me like Bezalel. And I believe there's a God in heaven. And I believe that he answers prayer. I believe that that's what he does. Okay?
Thank you so much for that enlightenment, Professor To. We would like to conclude this lecture. Thank you so much, everyone, for joining our lecture today. And thank you, Dr. To, for taking your time out for us very early in the morning. I believe it's 9 a.m. there.
Yes.
Thank you all for coming. And we will be back as GSA with more events. So thank you. Stay safe, everyone, and have a great evening.
Thank you.
Thank you.